What we're going to start today and what we're going to spend really the next few weeks on are logarithms. Logarithms are going to be really important for you going forward. You'll see them again in pre-cal, and you're definitely going to see them in calculus, especially when we get to natural logs. So what we're going to do to start is we're just going to look at some exponential equations. So something like this first one, if I have 2 to the x equals 4, well, I can figure out pretty easily that x is 2. All right, if I have 2 to the x equals 8, I can figure out pretty easily that x is 3. The reason I need something called a log is because of an expression or an equation like this one. Now that's something I can't really figure out. I don't know what power I would need to raise 2 to in order to get 6. So this is where logs come in. Logs are basically the inverse of an exponent, and they allow us to be able to evaluate and find basically that missing exponent. So the way a log works, if you look over in our box, a log is it's the inverse of an exponent. Log, that little b, or that little number that's down there, is called the base. All right, so the little number is the base. The number that follows, what you're actually taking the log of, that is called the argument. You may have heard that word back when you did your SOHCAHTOA stuff, like if you had the sine of 3x, or you had the sine of 37 degrees. What came after the sine, that was also called the argument. Okay, so that's what it's called for log as well. And then the x is the exponent. Now that helps us whenever we convert, because when you convert this to an exponential expression, the base of the log is still the base of the exponent. And that's what makes them pretty easy whenever we convert them. Now, a couple things. This is actually not a typo. That's the abbreviation for if and only if. And that's something, if you didn't see it in geometry, you'll see it come back up a couple times. So when it comes to logs, one thing we need to know, the argument has to be greater than 0. So if you guys remember when we did square roots, what was under the radical had to be greater than or equal to 0. But when we get to logs, whatever our argument is, basically cannot be negative. I cannot take the log of negative 2. Okay, that's not possible. I also can't do the log of 0. And that, if you think about your graphs, it kind of makes some sense. Think about the exponential graph. Okay, looks like this, has that horizontal asymptote. Well, if these are inverses of each other, if I switch x and y, I now have a vertical asymptote, and that's going to be the shape of the log graph. So as you can see, the domain there, we have to have that argument greater than 0. The base is not going to be 1, just because, again, that's not going to be a log function. That's just going to be exponential, because 1 to the anything power is going to be basically 1 every single time. That base is also going to be greater than 0. And that's it's possible to have a negative there. Again, it doesn't correspond to an exponential function. Because when we talked about exponential functions, we didn't have negatives as bases because we couldn't raise that negative to a power and actually get that function. Remember, we said it would bounce back and forth with odd and even numbers. So that's just a few things. Out of all of those, the biggest things to know, what we were taking the log of is called the argument, and then that argument has to be greater than 0. All right, so let's go ahead and actually just start practice converting these, because this is what we're going to use the most often. In order to evaluate a log, most often we're going to just convert it to exponential form. Or to solve an exponential equation, we're going to convert it to log form. So what we do is we start with the base. The base is the little number of the log. Okay, the base of the log is the base of the exponent. So the base of the exponent is what actually gets the exponent. So basically you write the base, and then really you flip the other numbers. The other way you can do it, what I usually tell my kids, I start at the base, and then I go in a little circle. So 6 to the third is equal to 216. So same thing on the next one. 7 is the base of the log, so 7 is the base of the exponent. So 7 to the 0 is equal to 1. 21 to the 1 is 21. 1/5 to the negative 1 is equal to 5. So one thing you'll notice in this unit as well, exponent rules are going to be really important. We need to be really comfortable with both our exponent rules, with negative exponents, fraction exponents, and all those things that we've done previously. All right, so now we're going to take an exponential equation, and we're going to rewrite it into a log equation. So again, the base of the exponent is the base of the log. So this is going to be log base 9. And then again, we either go in a circle or we just flip the numbers, whichever way you want to look at it. So log base 9 of 81 is equal to 2. Log base 20 of 0.05 is equal to negative 1. So 20 is the base, 0.05 is the argument. Log base 16 of 8 is equal to 3/4. And log base 15 of 1 over 225 is equal to negative 2. So when it comes to rewriting these, again, the biggest thing to remember, the base of the log is the base of the exponent, and those are going to be the same. So let's go back to our original problem now. So now, if I wanted to actually solve for x here, what I could do is I could rewrite this as a log. So this would be log base 2 of 6 is equal to x. And now I can find what that missing exponent is. Now something like this, we would evaluate with a calculator. So part of what we do today will be with a calculator. All right, so let's go ahead and actually evaluate logs. So to evaluate logs, what we're really doing, think about it as this equals x. Now it's not an equation, we're just evaluating it, but that really what we're trying to find is the missing exponent. So in exponential form, 4 to the something is equal to 64. So I'm trying to find that missing exponent. Well, 4 to the third power is 64. So log base 4 of 64 is equal to 3. All right, look at the next one. Log base 8 of 1 over 64. So 8 to the something power is equal to 1 over 64. Well, let's think back about our exponent rules. In order to move something to the other side of a fraction, it needs to be a negative exponent. And then 8 squared is 64. So log base 8 of 1 over 64 is negative 2. All right, 81 to the something power is equal to 9. So to figure out what that power is, again, this time that number is getting smaller. That means I'm taking a root. So remember, whenever we take roots, those are fraction exponents. This would be a square root. Square root as an exponent is 1/2. All right, and then looking at the next one. Log base 1/3. So very similar to B. 1/3 to the something power is equal to 27. Well, to go from a fraction to a whole number, I need a negative exponent, and that would be 3 to the third. The next one's a little bit trickier. 27 to the something power is equal to 81. Now, if you're really good with your mental math and your exponent properties, you might be able to figure this out without showing any work. You may be able to realize, hey, I could take the third root of 27 and raise it to the 4th power. Well, third root, roots go on the bottom, power goes at the top, that would be my exponent. But that's not as intuitive for all of us. So if that's the case, what we need to do is we need to rewrite these two numbers with the same base. And this is something we're going to do when we get to solving exponential equations. So this is a really helpful strategy going forward. So 27 to the x, I can rewrite as 3 to the 3x. 81, I can rewrite as 3 to the 4th. Well, if 3 to the 3x is equal to 3 to the 4th, 3x has to equal 4. So that exponent is 4/3. Again, the better you are with your exponent properties, the easier it'll be for you guys to be able to kind of figure these out maybe without going through those extra steps. All right, then this last one. 5 to the something power is the square root of 125. Well, I don't know the square root of 125, and I need to write these in terms of the same base. So let's start by rewriting this as 125 to the 1/2. Well, just like we did with our radicals unit, I want to rewrite 125 with the same base. 125 is 5 to the 3rd. 5 to the 3rd to the 1/2 is 5 to the 3/2. So that means that missing exponent would be the 3/2. Now with logs, there are a few special bases. So there's two bases that you actually won't ever see. So if you see just regular log, and this is the button you'll see on your calculator, regular log without a base written actually does have a base. That's called the common log, and it has a base of 10. So we can still evaluate this. This means 10 to the something power is equal to 1,000, and we know that that's going to be 3. So the log of 1,000 is 3. 1 over 100, 10 to the something power is 1 over 100. To make it at the bottom of a fraction, it would be a negative exponent, so that's negative 2. The next one, 10 to the something power, is 100 to the 1/3 power. So again, let's rewrite that as 10 to the 2/3 power. So this is going to be 2/3. Now another one that's going to be really important for you going forward in calculus is the natural log. So you will never see log base e. You'll never see that written. If instead you see ln, that is going to be our log base e. That's really what it means. So ln stands for natural log. And that natural log is because it's using the base of e, that Euler's number that we talked about at the beginning of the unit. So ln is going to have a log of a base of e. So ln of e, to evaluate that, that means e to the something power equals e. Well, that has to be 1. On the next one, e, and that's the problem number as well, but e is also my base. So e to the something power is equal to 1. So in order to make anything 1, if I raise it to an exponent, that has to be 0. And those are these 2 log properties that are listed over here. All right, if you have log of any base and the argument is the same, that's going to be 1. If you have a log of any base and an argument of 1, then that's going to be 0. That works for any log, natural log, regular log, whatever else. So looking at the next one, e to the something power is e to the 7th. So again, this one would just be 7. I shouldn't say x equals because it's not an equation, but adding that x there really helps us to be able to simplify these. All right, so the last thing we're going to do is we're going to look at how to evaluate these on a calculator. Because some of these problems that we've talked about, we can't figure these out. So how to do these on a calculator, let's go ahead and get them out. So just a reminder, if you do not have a calculator of your own, you do actually have a calculator on the iPad. Directions for how to access that are posted on Schoology. There's also a video that Miss Belch made that kind of walks through how to get that as well, that you can look at. But there is an app on your iPad through VMware that you can use to get this same little Casio emulator that I have, so you can kind of learn how to do this without having a calculator on you. All right, so if I want to use regular log or natural log, both of those buttons are pretty easy to find. So regular log of a base 10 is over here. ln is right next to it. So ln is right where e to the x was, and log is right where 10 to the x was. So if you ever forget the base, it's written right above it. Now the problem is a lot of the logs we're going to use don't have a base of 10. There is a change of base formula that we're going to learn later on in this unit. But before we even get there, which you can do to make your life a little easier, if you go to F4 where it says math, you're going to see the option under F2 that says log AB. And this log AB is how we enter a log of a different base. So if I want to evaluate log base 3 of 7, I now have that option. So log base 3 of 7 is 1.77. ln of 4, ln is just the regular ln number. Again, the base is implied. It's not written, but it is implied. If I want to do the natural log of 3e, so I would do ln, I'll go ahead and put some parentheses, 3, and then shift ln for e. Again, it automatically gives it an exponent. Since we're just doing e, I'm going to make that exponent 1. So the ln of 3e, there's my value. Then on the next two, we actually need to write those in log form in order to evaluate them. So 2 to the x equals 6. This would be the first one we had at the very beginning here. The base of the exponent is the base of the log. Switch the other two numbers. Same thing on the next one. This would be log base 10. Well, if the base is 10, we don't need to write it. And then I'm going to add one more problem here that I meant to include on your notes. So go ahead and include e to the x equals 7. So if I wanted to evaluate this, to figure out what x was, I would rewrite it in log form. So this would be log base e. But again, I'm never going to write log base e. You're never going to see that. Instead of log e, I'm just going to do ln of 7. So now I can go to my calculator and I can plug in all these values. Now when I go to my calculator, I'm going to lose what's written down here, but log base 2 of 6. So log AB, log base 2 of 6. And again, you can check to make sure that's true. Hey, 2 to the answer does in fact equal 6. When it's not rounded, it ends up there exactly. For problem E, okay, that was log base 10, so I don't need to write it, log of 14. And then the last one that I had, ln 7 is 1.94, we'll round up to 9.946. But again, if I want to know exactly, if I check my answer, e to the answer does in fact equal 7. All right, now I know there are a few of you who are using TIs. If you're using TIs, you do have a log base as well. The way you get there, if you do alpha and then window. So alpha is that green button, and then Windows at the top over near y equals. You're going to get a menu that looks like this, and you'll see log base. Once you use that, then you'll be able to type in your base and your